Hello, the purpose of this screencast is to go through the Module 13 homework for your PSS 302 class. Remember that your exact problems on your assignment might not be identical, as in the values might be different, but the logic behind solving the problems will always be the same. So let's see, on this particular version of the assignment, the first problem is asking us to compare a traditional lengthy battery of cognitive tests that are used to determine whether somebody might show symptoms of Alzheimer's disease with this newly developed test called the 7-minute screen. This would be time-saving if researchers could show that the test scores are comparable. So the problem is asking us to run a correlation to see whether scores on the 7-minute screen relate to scores on the traditional cognitive series test. The key thing to remember here is that the scores in and of themselves don't necessarily matter, just that like lower scores on the 7-minute screen would correlate with lower scores on the cognitive series and so forth. Okay. So to test the hypothesis, we would go through the 4 steps of hypothesis testing. The first step is to identify the 2 hypotheses. The trick here is that to remember for correlation, we're always testing that the correlation equals 0, meaning that there's no correlation at all. So that the null hypothesis should always be that R equals 0. And then the alternative should indicate whether we're predicting a directional, where we're saying that like the correlation will be negative or less than 0, or positive greater than 0, or non-directional, not equal. So use symbols to state your hypotheses following the example in practice problem 15.1. So you will notice, by the way, that this assignment is very, very similar to practice problem 15.1. All right, next determine the critical region. We've done this for several statistical tests. For this particular one, it's asking us to calculate the Pearson product moment correlation, and we can find those values, critical values, in the Pearson correlation table found on page 657 of the textbook. So look at the problem to see what you're testing. We need the two-tailed test. Alpha is set at 0.01 in this particular problem. Double check your assignment to make sure that it's asking you the same. And so you would just use the table following the model in practice problem 15.1 for looking up the critical value. And that is part 2. The degrees of freedom for correlation, you do need degrees of freedom, and it does remind you in that table on page 657, degrees of freedom are n-2, where n is the total number of participants, not the total number of scores. So to get that, basically, in this example, we would count up the number of patients. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 patients here. And degrees of freedom would be n-2, or 9-2. Okay, so that's the critical region. Now we have to compute the test statistic. Here is the formula that we're going to use. It looks pretty ugly, so make sure that you write your formula out, including all the steps. And the trick here with solving any of these correlations is making sure that you are very, very careful with your calculations in your records. So I'm going to give you a little tip for that. I'll also note that in practice problem 15.1, it gave you this R formula. We're going to see this later as actually R sub xy, and that'll be important later when we're solving like partial correlation. Excuse me, but R without anything is R sub xy. So those are the same formulas. To do this, we're going to have to calculate the pooled variance values here, and there's the formula for that. We're going to have to get sums of squares for x and y separately. There's the formula for that. So these formulas should look quite similar to our original sums of squares formulas that we calculated way back in Module 6 in this class. And my best tip for doing this is to follow the example in the practice problem 15.1 and where you use the table to keep very careful records of your values. So here's your X values are the 7-minute screen, Y values are the cognitive series. Go across the table, get the squares, right, for each value. So 3 squared is 9, 8 squared is 64, and so forth. Do the same thing for Y squared. 11 squared is 121, I think. I can't do the rest in my head, but you would do that. X times Y, you would multiply 3 times 11 to get 33 for your X times Y values. And then you're going to need the sum of all of these values, so sum all of the columns, including X, so that this is sum of X equals, and then you're going to get sum of X squared equals, you're going to get the sum of Y equals here, the sum of Y squared equals here, and then the sum of xy equals here. And if you follow that model, then you should be able to easily plug in the numbers, right? So that this should start to look familiar. You're going to need sum of x squared, then you're also going to need the sum of x, and then square that value, and so forth. It's a sum of xy. So okay, so that should be pretty straightforward. Just plug in your values. Again, the critical thing here is just be careful. Use the table, map everything out for yourself, and make sure that you're double checking all your values. Then step 4 of hypothesis testing is we're going to use that test statistic to make a decision. We're going to interpret the decision. And so we looked up R critical in step 2 above. If the R obtained is greater than R critical, we can reject the null, just like we've been doing with all of our hypothesis testing in this class. All right, the last portion of this question is asking us to answer what percentage of variance for the cognitive scores is predicted from the 7-minute screen scores. So if this hasn't been clear to you yet, this is what the R-square effect size measure is telling us. So this question is literally telling you to compute the value of R-squared. Well, remember in previous chapters, R-squared, we needed T, and then we squared that and divided by degrees of freedom. Well, here we don't have T, but we have R. And as the name suggests, we literally just need to square that R value. So that R squared is literally just the square of R obtained, the one you calculated above. So calculate that value and then interpret it. All right, that's the first problem. Number 16 is giving us a situation, right? Let's say that a researcher already calculated a correlation coefficient. They got R equals 0.60 from a sample with 10 participants. There are 2 parts to this problem. They're asking different things. Part A is asking if n equal 10 is a sufficient sample size to conclude that there's a significant correlation. So you're going to run a 2-tailed test, alpha equal 0.05, your n is 10, and your R obtained is 0.60. So look up the critical value for R and then make your decision, being sure to specify what critical value you found with these parameters. And then B is the identical question, it's just now the n is changing. Here n equals 25, not 10, and answer that question. So that should be pretty straightforward. Okay, the next problem is number 18. This problem is challenging because it's asking you to calculate a partial correlation. Partial correlation requires that you calculate all of the other combination of correlations before you get to your partial. So you're actually going to have 3 total correlation values here. This problem is virtually identical to practice problem 15.2. So how we're going to do that is first we're going to have to calculate the correlation between variables x and y. And so that's this RXY formula, the same one we just used. And then we're going to have to calculate the correlation between x and z. It's the same formula, but instead of x and y, we're using x and z. Now, if you calculate sums of squares x above, you can use it. Here, it's the same x. It's just you'll need to get the z. And then we'll also have to calculate our xy dot z, which is the partial correlation. It's the correlation between x and y while holding z constant. And here's the formula for that. So a couple tips and tricks for this. Key here again is staying organized. Use the table just like it was demonstrated for you in practice problem 15.2. These were the number of participants, right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 participants in this. So we'll just say number of scores, and the total here would be 12 total scores, right? So n equals 12. And again, double check that your assignment is the same. The numbers are probably going to be slightly different depending on which version of the assignment you are working with in your class, but the logic is always going to be the same. So here, just make sure that you're calling the first variable x, which was number of crimes, second variable is y, third variable is z. Here you're going to need to get x squared values, y squared values, and x times y values. Then you're going to need to get z squared values, x times z values, and y times z values. So just keep careful records of that. And then down here, we're doing the sum of x, right? And then this would be the sum of x squared. This is the sum of y, the sum of y squared, the sum of xy, the sum of z, the sum of z squared, the sum of xz, and then the sum of xy. And again, to calculate these, right, you're just gonna, here we're gonna square the x value, right? So 3 squared is 9, 4 squared is 6, what is 4 squared? 16, right? And so forth. Y, same thing, we're gonna do y squared, 6 times 6 is 36, 7 squared is 49, and so forth. X times y is x, 3 times 6, right? So 3 times 6 is 18. Oops, wrong column. 3 times 6 is 18. 4 times 7 is 28. So we're just doing that math. Here, z squared are the z values, right? So 1 squared is 1. 1 squared is 1, and so forth. X times z, we would just carry that across. So 3 times 1 for this column. Y times z, y was 6, 6 times 1 is 6, and so forth. So you just fill in these numbers, do all your math down here so that you're getting these solutions, and then you should be able to plug in these formulas quite easily. Remember that in the partial correlation formula, you do need the values for all the other full correlations to put into the formula. So you do have to solve rxy, rxz, so that you, or sorry, rxy, rxz, and ryz, so that you have everything to put up here. And then here, this might be a little bit confusing, but basically you're going to get this xz correlation. You're going to square that and then subtract it from 1. So for example, let's just say my r squared, and let's say r lower, oh, sorry, I guess if I typed r squared, r squared xz, let's just say it was 0.49. So then the value that I'm going to put in there is going to be 1 minus 0.49 squared, and I will superscript that so that it's more obvious to you, which is going to be 1 minus 0.49 squared. Now I need my calculator. 0.49. Oops. 49 squared, 0.2401. And then I would just do that math. So just make sure that you understand what what this means, because I get that that's a little bit confusing. Okay, so then just interpret what your obtained partial R value means. And again, follow the example in practice problem 15.2 because it's virtually identical to this one. Okay, our last problem on this assignment is number 20. And this one is different from the previous two. The first problem was asking for the Pearson product moment correlation. The second one was asking for a partial correlation, which to calculate also required getting 3 other Pearson correlations. This problem is asking you to compute the Spearman rank order correlation. This one is different. It is challenging to do by hand, I'm not going to lie. It will take you probably a couple of hours, and you will want to be very focused and very careful as you're going through rank ordering all of these. That is usually where the mistakes come, is rank ordering these variables. So I'll walk you through how to do that. Note that for the Spearman correlation, we are looking at a different table to get critical values. In our textbook, it is on page 658, and this is for the Spearman rank order correlation. Okay, so what we first need to do, and this, by the way, is following exactly the example of the part 1 of practice problem 15.3. Okay, so we're just going to take each variable individually. In the first one, we're going to rank order each value for social status, where 1 is the lowest, following this example. And when I say 1, I mean the lowest value of the rank, and that would correspond with the lowest value in the data. So while social status actually does have 1s in it, learning score doesn't. But the lowest score here, 3, in learning score would be a rank order of 1 because it's a lowest score. Okay, so how I do it, and again, this does take me a while, I have to be super careful, is I keep the original data here in the column. And then I reorder them according to because remember how when we were calculating median, we had to like order the scores from lowest to the highest? To do these Spearman rows, you have to do the same thing. You have to order from lowest to the highest. So, and account for duplicates, just like we did with the median. So the lowest value in this data set I have is a 1, and I put that in the first row because I know that's going to be my lowest rank. And then I go with the 2s, and I list each 2 that I have in the data set. This data set had 3s. I had 2 number 3s. 4s and 5s, and all I'm doing is just taking these values right here and putting them in their rank order here in parentheses, so that when I'm doing the initial rank, I am ranking the number in parentheses, and I'm taking note of all the tied scores, right? So that I have 10 scores in this data set. If each of the 10 scores was unique, right, there were no ties, the rank would be 1 to 10, low to high. When I have ties, though, I need to count them in the initial rank or the tentative rank that is illustrated on the practice problem. But I'm going to have to actually adjust that in the final rank. So in my initial rank, I want ranks equal to the total number of scores in the sample. But I want to indicate where the ties are as best as I can. So for example, number 2, I had 3 number 2s. So rank 2, 3, and 4 are tied. That means I'm going to have to take the average of that to get the final rank. And the final rank of the average of for every number 2 score, every score of this value, it just happens to be a number 2 in this data set, would get the final rank of the average of the ties. So let's see if that makes sense. Let me try it another way. So I had 1 number 1 in this data set. That got a final rank of 1. I had 3 2s. So my rank order, 2, 3, and 4 were tied. I take the average of that, and my rank order here is 3. Now my next rank order should be a 4, right? But I have another tie. My next value is a 3, and there's 2 3s, and so those are tied for position 5 and 6 in the rank. So I have to take the average of that, 5.5. Now my next rank should be 7, because this should have been 5 and this should have been 6, right? If I'm looking at the initial rank. I have a tie again, though, for position 7 and 8. I had 2 4s there. So I got to take the average of that, 7.5. My next value should be 9, right? But I have a tie again. I have 2 number 5s. So I take the average of that. And so my final ranks then are 1 through 9.5 with my duplicates indicated. Okay, let's do that again because I know that's super confusing. Let's do a learning score which has no 1s, right? And the scores are quite a bit different. So here's the actual learning score. What I'm going to do is keep the learning score and then rank them from lowest to highest here, also indicating any duplicates, right? So in position 1, I had my lowest score was a 3 and I had 2 3s. My next score was a 4, my next was a 7, my next was a 10, an 11, and 12. I had 2 17s and I had a 19. And again, all I'm doing is reordering these values right here and putting them in a rank order right here. However it makes sense to you, it did not make sense to me to erase these original learning scores because then I didn't know which ones I had already accounted for, if that makes sense. Anyway, okay, so my initial rank has to be equal from 1 through 10 to my total number of scores here, which was 10. So if these were unique numbers, their ranks would be 1 through 10. Some of the numbers are unique, others are not. For example, I have a tie in position 1 and 2. So I'm going to take the average of the rank, right? Not the average of the value, but the average of the rank. If this should have been 1 and this should have been 2, but they're tied, to indicate that tie, they each get a 1.5. Then my next rank would be 3. There's no tie there, so it is a 3. Then 4, 5, 6, 7. I don't have another tie again until position 8. And because there are 2 there, I need to take the average of 8 and 9. So I have 8.5 to account for positions 8 and 9. And then my final rank is also untied and winds up being a 10. Okay, think about that. Go back, try to rewatch this video. I know it's going to take you a while to try to process that, but yeah, just be real careful when you're doing that and double check the actual values and numbers on your assignment because they're probably not going to be identical to this. Now here comes the super tricky part. We have to realign the ranked scores with their participant scores. Here's where it gets tricky. Again, a lot of mental effort, a lot of thinking about what the scores mean, a lot of double checking, writing things down on a piece of paper to keep track of what is what. But if your original score is a 1, you have to, to realign these ranked scores, you have to look at the original score and then look at the new assigned rank. So this takes a lot of double checking. Let's go to social status first. So my original data set, this is the original data set, and here's where I'm going to rank those. In the original data set, subject A had a social status score of 1. If we go back up here to where we ranked, the final rank for social status score of 1 was a 1. Now for the next one, our social status score for subject B was a 3. To get that rank, I have to go back up here and look in the social status column for scores of 3, right? And here, the scores of 3 are these ones in parentheses, and I have to look across to see what their final rank was. If they got a score of 3 on social status, their rank is actually a 5.5. And so I put that into this social status rank column. C had an original value of 2, so I have to go back up to my social status column and look for where the 2's started falling. There were ties. Go over to their final rank. Everybody who got a score of 2 got a rank of 3. And so everywhere here where I see a 2, their social status is going to be a 3. Now I just looked up the score of 3 and the rank was 5.5, right? So I can repeat that here. Now here their score was 5. I need to go back up to my final ranking on social status, look for the number 5 in this first column. Here it is. Their final rank for the people who scored a 5 on the social status test is 9.5. And so you see where we're putting 9.5 by all of the 5 values. Okay, so just again, it's really tough. You have to think about it a lot. You have to keep double checking your scores, but that's what you're doing here when you're realigning. And again, just follow the model of practice problem 15.3. Then once you fill in all of these rank orders, you're going to have these social status ranks by subject matched with their learning rank score by subject so that their actual scores are staying together so you can run a correlation. And then you're going to use actually the same old Pearson formula for R sub xy, the same old one we've been using, except now you're going to use the rank for social status as factor x, variable x. You're going to square that. Then your learning score rank is going to be variable y, and then you'll just want to get these totals just like you were doing before. So 1 squared is 1, 5.5 squared is, I think it's 25.25 maybe. Don't judge me on that, I don't know. 1.5 is 1.25 maybe. And then you would just multiply these, so 1 times 1.25 is 1.25, and so forth. So you would just do this math, get your sums down here, just like we were doing before. So we're going to get EX values here, EX squared values here, EY values here, EY squared values here, and EXY values here. And then you can just plug in those numbers into the formula and solve for your correlation and then interpret that by looking up your degrees of freedom on page 658 to get your critical value. Okay, this was a super long video. There was a lot to go through. There's really only 3 problems. They follow along identically with practice problem 15.1, 15.2, and 15.3. But if you have any questions, reach out to your professor for help.